Welcome to the Explainer. We are jumping right into part 3 of our 12th part masterclass today, and let me tell you, we're exploring an absolutely epic trajectory. We're looking at the transition from historical mathematics all the way down to the modern, ultra-rigid silicon grid of GPU programming. We're going to see how humanity has constantly, throughout history, tried to take our messy, continuous reality and force it into perfectly explicit, formalized boxes, and how that exact same drive is powering the bleeding edge of artificial intelligence today. To really understand where we're going, we have to start by asking what is arguably the most fundamental philosophical question in modern computing. How do we translate fluid human thought into rigid silicon? Think about your own mind for a second. Our internal cognition, what researchers sometimes like to call OS alpha, is incredibly fluid. It's continuous, it's associative, and it's deeply intuitive. But the hardware of a microchip, it is the exact opposite of that. It's cold, it's strictly mechanical, and it demands absolute deterministic exactness. So how on earth do these two totally alien worlds actually connect? Well, the answer is brilliantly captured by this famous idea that we are quite literally tricking rocks into thinking using lightning and text. It's wild to think about, but text serves as what we call a semiotic bridge. It's this magical translation layer that allows us to map our nonlinear associative human imagination directly onto a physical silicon substrate. By using highly structured text, like programming code, we can enforce our fluid intent right onto the unyielding physical reality of a processor's logic gates. Which brings us nicely to our first major concept, the semiotic bridge. To really grasp how we program modern AI using this bridge, we actually have to look backward. Picture the 17th century. For millennia, European mathematics was severely limited by what was basically a mathematical straitjacket. In classical geometry, an equation was treated as a literal physical dimension. If you wrote a squared term, it literally had to represent a physical 2D area. But then, geniuses like Descartes and Pierre de Fermat sparked a massive paradigm shift. They created analytic geometry, which completely broke us out of that restrictive box of physical shapes, pushing us into the liberated, boundless world of abstract algebraic symbols. Math was finally freed from the tangible world. Fermat actually pulled this off with a concept he called inadequacy. He essentially formalized continuous geometric space into discrete algebraic steps. By temporarily using tiny algebraic parameters to approximate continuous curves, and then mathematically setting them to zero, those parameters just vanished, leaving behind an exact calculation. He mapped continuous physical space onto strict mathematical grids, and that practically handed us the keys to calculus. All right, let's fast forward to right now and look at taking that math straight to the silicon grid. That exact same historical drive to formalize math perfectly maps to how we control modern GPUs today. See, for years, GPU programmers were trapped in the SIMD paradigm, single instruction, multiple thread. In this model, the human programmer had to painstakingly micromanage the absolute chaos of thousands of individual hardware threads. You had to figure out exact memory layouts and synchronization, and honestly, it was brutal. But now, we've shifted to the tile model. Here, the programmer steps back. You simply define high-level operations on multi-dimensional blocks of data, called tiles, and you let the compiler handle the chaotic mapping of threads to hardware. But why the big switch? Well, we hit what's known as the SIMD bottleneck. As GPU hardware evolved, especially with the introduction of massive tensor cores starting with NVIDIA's Volta architecture, that old SIMD model became a severe bottleneck. The mental gymnastics required just to keep the silicon fed with data became totally unsustainable. To solve this, NVIDIA introduced Tile IR. Think of Tile IR as a portable virtual machine and a virtual instruction set architecture. Instead of pretending the GPU is just a collection of independent threads, Tile IR natively models the GPU as a tile-based processor. It automatically handles the mapping onto hardware resources, the memory hierarchy, and the tensor cores. It takes that immense burden completely off the programmer. Of course, this shiny new abstraction comes with some heavy trade-offs. Let's talk about rigid tile semantics. We are quite literally forcing continuous AI math into highly restrictive computational boxes. To guarantee exact, deterministic execution, the Q-tile programming model imposes incredibly rigid semantics. The shapes and data types of your tiles, they must be absolutely known at compile time. There is zero guessing at runtime. Plus, tile dimensions are strictly forced to be powers of 2. They also use value semantics, meaning a copy of a tile is completely independent. By stripping away all that messy runtime variance and enforcing these rigid mathematical constraints, the compiler can generate perfectly specialized, hyper-fast machine code. So, if the silicon demands these unforgiving rules, who actually bridges the gap? Enter the human pilot using Helion. Since the hardware requires such rigid rules to operate efficiently, how does a human safely and easily express their fluid intent? Helion is the answer. Helion is this absolutely brilliant domain-specific language built right into Python. You can think of it basically as PyTorch with tiles. It acts as our ultimate semiotic bridge. It allows human pilots to use the standard, familiar PyTorch syntax they already know, while a powerful auto-tuning compiler silently crafts the rigid, optimized tile IR underneath. Helion totally strips away the brutal math of memory mapping. It automates all the incredibly complex tasks like tensor indexing, calculating strides, and setting up grid sizes. It even generates massive implicit search spaces, testing hundreds of configurations to find the absolute fastest execution path for your specific hardware. It elevates you from a line-by-line coder sweating over thread synchronization into an algorithmic orchestrator who just declares their high-level intent. And that elevation points perfectly to our ultimate goal here, orchestrating deterministic execution. By leveraging tools like Helion and Tile IR, we can actually trace this formalization process layer by layer. We start at stage 1 with our associative human intent written in Python and the Helion DSL. Then it drops down to stage 2, into abstract tile operations via CUDA_tile. Down to stage 3, where MLIR dialects handle explicit, scheduled memory allocations. And finally, we hit stage 4, PTX and SOS. These are the lowest-level assembly languages commanding the GPU hardware directly. You're literally watching messy, high-level Python code get systematically stripped of all its flexibility until it hits these unyielding physical machine instructions. This gives us a very clear 3-step process for modern computing. First, the human applies their associative intent. Second, the compiler system acts as a deterministic scripter, locking that intent into a rigid text template. And third, the hardware executes those instructions with perfect arithmetic logic unit, or ALU fidelity. By compiling our models this way, we completely fire probabilistic guesswork out of the runtime loop. The processor only executes mathematically absolute, fully auditable commands. No surprises. So why does all this matter? Because absolute hardware-level determinism gives us rock-solid reliability. In a world increasingly obsessed with unpredictable, probabilistic AI, we desperately need systems that do not guess and do not hallucinate when executing critical tasks. By eradicating runtime variance, every single decision traces back to a specific auditable line of code. This is exactly how we achieve the safety required for healthcare compliance, critical cloud infrastructure, and ultimately our moral safety as engineers. The gap between our fluid minds and the rigid hardware is shrinking fast. And as our compilers do more and more of the heavy lifting, I want to leave you with this final, vital thought. In an era dominated by lossy, probabilistic AI, will you actively use the semiotic bridge to author the deterministic rules of the future? Or will you surrender control to the probabilistic machine? The choice of how we build our infrastructure is entirely up to us. Thanks for joining me on this explainer, and keep learning.